Start recording. Sorry about that. So simply put, the dots, they represent the Lewis dot structures for the atoms, and those dots represent the valence electrons. Now, with respect to compounds, it's a little bit different procedure. You would need the shapes table, and let me pull that up real quick. Okay, the shapes table right here is the one that we're going to use once we figure out the structure. Okay, and by the general formula, you notice the first column, we have a very general formula labeled A, B, and E. A represents the central atom. B represents what is bonded to the central atom, whatever atoms are bonded. They can be the same or they can be different, okay? And E represents the number of lone pair of electrons that are on the central atom. So once we come up with a structure using the Lewis dot structure, we can assign it a general formula, ABE, okay? And then from that information, let's say, for example, we assign the structure AB4, subscript 4. That means A is a central atom, and there are four elements bonded around the central atom. Well, that particular structure would have the molecular geometry in the second column, three-dimensional there, that picture. And that has this very specific name that is called tetrahedral, okay? And then there's a bond angle there that represents a bond angle between two of B's relative to each other. And that bond angle in the last column is 109.5. That is the maximum. That's pretty standard with respect to the structures of compounds, tetrahedral. And that is the maximum amount of bond angle between the B's, because remember, these lines between a central atom and B represent a bond, and those are electrons, two electrons. Well, there's four of them, four pair around the central atom, and they want to separate from each other as much as possible. And that is, under these conditions for that structure, that is the optimum bond angle between B's, okay? You can notice there's a variety of different structures, okay? And so with that information, ABE, we'll be able to figure out what it is, what is the geometry, what is the shape, and what is the bond angle. So let's go back to the slide where we go through procedure and how to figure that out. Okay, you'll be given a formula and you'll be told which atom is the central element. That means that that's the guy in the middle, whatever it is, and then everything else is attached relative to the central atom. Then the other aspect to remember is the octet. Okay, we want to put them in such a way that is the valence electrons. So there are 8 valence electrons around everybody except hydrogen. Hydrogen does not follow the octet rule. Its rule is a duet. Okay, so once you make a bond with hydrogen, that's it for hydrogen. You can't add any more electrons to hydrogen once it's bonded. So we tally up the number of valence electrons that every atom brings to the structure, okay? You're told what the central atom is, and so we can very quickly, given the structure, draw the central atom, and then draw all the other atoms bonded to the central atom. We can quickly draw a line. The line represents a bond of 2 electrons, okay? And then, keeping in mind what I just said about the octet, we want to maintain the octet around all the elements except hydrogen, because it's a duet for hydrogen. And then we go back and we make sure that we still have the total number of valence electrons that we calculated, and that comes from the periodic table. Once we know how many valence electrons we have total, that is what we got to work with, okay? We can't, arbitrarily just add electrons or arbitrarily remove electrons. So we got to make do with what we have. You will always end up with a number that is divisible by 2, which makes it pretty um, makes it good, because you now, instead of having to deal with individual electrons, you can just deal with pairs. Okay, a pair of electrons. It makes it much easier as far as the accounting of all the electrons, because you can end up with 32 valence electrons, and you can sit there and count each and every one, or you can simply just draw a line, and that line represents 2. Now, once you make the structure, identify the bonding electrons. Those are the electrons that are bonded, where you got 2 different atoms that are bonded to each other. And then on the all the electrons, identify what we call the lone pair. These are electrons that are not bonded to anything. They're just sitting there on an atom, either on the central atom, or they could be sitting on whatever is bonded to the central atom. Now, sometimes, like I said, you got 8 valence electrons, you got to work with that. So when you start counting the octet and nothing, you don't have enough valence electrons, then we start taking lone pair electrons and making double bonds, and then checking the octet and see if that works. If that doesn't work, we go all the way up to triple bonds. Okay, so we create, with the valence electrons we have, either a double bond or a triple bond, until such time that you have the octet fulfilled around everybody except hydrogen. All right, so let's take an example of H2O, very straightforward molecule. Okay, first thing we do, we count up the valence electrons. So again, if you don't remember how many valence electrons, you go up to the periodic table, find its position, look at the group number, and this is only true, I can't overemphasize, only true for the A metals. Roman numeral 1A all the way across to Roman numeral 8A. The B, the transition metals, we cannot predict the valence electrons. Okay, so oxygen brings in 2, hydrogen brings in 1 apiece, and there's 2 hydrogen atoms, so we have a total of 8 valence electrons. And this is where then in my case, I like to take those valence electrons, and guess what? I can take that 8 and divide it by 2, and that gives me 4 pairs to work with. Okay, so you can do the individual electrons, but you can just divide it by 2, and you got 4 pairs, and draw lines, and now you have an easier way to do the accounting. All right, so I got 4 pairs to work with. All right, so I draw the central atom, in this case is oxygen, and then I can very quickly, because I'm given the structure H2O, that tells me that those hydrogens are bonded individually to the central atom, and I can very quickly write that structure out. In other words, put the 2 hydrogens bonded to oxygen. What that does is that I can maybe do it like this. I can say hydrogen, and then I got a single line, and then I got oxygen, a single line, and I got hydrogen. Okay, well, that takes care of 2 pairs. Okay, and now that I have 2 pairs taken care of, and I'm allowed 4, I got to put the other 2 someplace. Okay, and the only place I can put them is on the hydrogen. Excuse me, let me correct that. The only place I can put them is on the oxygen. Why? Because the hydrogen's full. Okay, the hydrogen is sharing 1 pair, so its duet is happy. If we count the electrons around oxygen right now, we only have a total of 4. Okay, and so we got to put the other 2. We have no choice but to put them on the oxygen, and I can denote that by a straight line. Can you all see that? It's kind of a crazy straight line, but it's there. And so now count the pairs. I got 4 pair up there. Perfect. That is what I started to work with. Okay. That is what I have to work with. So now I have 4 pair. Okay. And so I can now, I had 2 pair when I started off, minus the 2 pair that I put in with the red line there. So now I got 0 pair to work with. Everything's fulfilled. Okay. I go back and check. Sure enough, I got 4 pair to work with. That is how many valence electrons. 4 pair times 2 is 8 pair. Excuse me, 8 electrons. Okay. Now at this time, identify the general formula. Okay. All right. So let me go back here from what I drew up here. This tells me here is I have around the oxygen's a central atom, so that becomes A. It's always A. The central atom is only one central atom, that's A. Okay. Then I look and see how many atoms are bonded around the central atom. Well, there's 2 hydrogens. Okay, so that is represented by the general formula B. Now I can't do subscript here, so bear with me. That 2 is a subscript. So it's AB subscript 2. Then look at the red lines that I put up there. There's 2 of them. Okay, those represent the lone pair on the central atom. So that is represented by the general E. Okay, recall the shapes table. We'll go back to the shapes table in a second. Now, how many lone pair do they have? There's 2 lone pair. So bear with me again. Subscript 2. So the general formula here, and that is equal to the general formula. Okay. Based on the structure that we came up with. That is AB2 is the general formula for the structure we just came up with. Now that you know the general formula, okay, you go back to the shapes table and look for AB2E2. Let's go back to that. Guess what? Where's it at? Right here. AB2E2. Y'all see that? Okay. That general formula came from the structure we came up with from the Lewis dot structure. Okay. So that tells us that this is an AB2E2, and there's a multiple compounds that have that general formula. Okay. Remember, A represents a central atom, and it's always going to be 1. B can be from 1 to 4 maximum, and E can be from 0 to at least 2, the number. Okay, and here now you can see the general molecular geometry 3-dimensionally. See the lone pair sitting there on the oxygen for water. Okay, and then the 2 hydrogens are represented by the 2 spheres right there. Okay, now that has a general shape called bent. Okay, now think about this for a second. There are 2 lone pairs on the central atom of oxygen. So there's a total of 4 electrons there with a negative charge. They repel from each other because they're negative charge. The result is that bond angle between the 2 hydrogens gets squished in. So that is why that bond angle that we just talked about earlier up here with tetrahedral, that bond angle gets much less than 109.5, simply because those lone pair of electrons force that bond angle to come in smaller. And it's no longer a starts with tetrahedral, but now it's called bent because of the lone pair. Something to put in long-term memory. Whenever you have lone pair of electrons on an atom, you're going to have a property that we call polar. We're going to have a lot more to say that. Polar species. Because basically, the covalent compounds, we have two types of covalent compounds. Earlier, we talked about the two types of bonds, ionic bond and covalent bond. And ionic bonds, if you recall, it's a full negative charge, full positive charge. It's electrostatic attraction with each other. With respect to covalent bonds, there is a sharing of the bonds. And sometimes it's an equal sharing, but other times it is not. There's no equal sharing. When there's no equal sharing, as far as let me restate that. When you have equal sharing, you have non-polar bonds. When you have unequal sharing, you have polar bonds. Good example, water and oil. We know that oil and water do not mix. Oil has non-polar bonds. Water has very polar bonds. They don't mix, okay? And so once we can identify the polarity, that tells us a lot about the physical properties. Classic example I use all the time in classes is makeup. Why? Some makeup is pretty tough makeup. You need some makeup removal. You can't really remove it with soap and water, right? Correct me if I'm wrong, but there's some hurricane-proof makeup out there that you need some pretty heavy-duty oil to remove. There's other makeup that, the tears, just the tears or water cause it to run. That has polar character, okay? But a lot more to say about that in the next chapters. So let's go back. So we identified the molecule of water to have the general formula AB2E2. There's the molecular geometry, the shape it has is called bent, and that bond angle is much less than 109.5. So let's go back to where we had. Okay. Okay, so now the hydrogens already have two, but oxygens two more. We have two lone pairs. We just went through that exercise and we come up with that structure right there. Okay? With the general formula of AB2E2. Okay, let's try some of these. All right. We have the first one, HCN, which is cyanic acid. It's a very poisonous gas. And then right now, don't worry about the structure and what they are. But you can notice there that you have carbon as a central atom for the first example. And then that means that hydrogen and nitrogen are bonded to carbon. Take the second example. We got carbon there. And then following the carbon, which is denoted as a central atom, we have a hydrogen and 3 fluorides. Okay. And then we have carbon dioxide with 2 oxygens around it. And then nitrogen, the last one, with 3 oxygens or 3 hydrogens around that. Okay, so we add up the valence electrons for HCN. Carbon brings in, let me do this. Okay, there's 1 hydrogen. Okay, so hydrogen brings in 1 valence electron. There's 1 carbon. Carbon's in group 4. So it brings in, 4 valence electrons. Okay. And then nitrogen is in group 5. Okay. And so it brings in 5 valence electrons. I'm going to denote that by VE, valence electrons. Okay. Well, we add that up, we have a total of 10 valence electrons to work with, or 5 pair. Okay. Let's first count all the valence electrons. Just do the second one. We have carbon again, brings in 4 electrons. Okay. Hydrogen brings in 1. And the fluorides is in group 7, right? All the fluorides in group 7, but there are 4 of them. And so it is 4, excuse me, what am I saying? 3 times 7. Okay, everybody see that? And so that comes up to what? 3 times 7 is 21, 22, and then the 4, check my math, I got 26 valence electrons. That sound correct? Or what's half of that? 13 pair. 13 pairs. Everybody see that so far? All right, let's do carbon dioxide, the third one. And so carbon brings in 4 again. Okay, we have 2 oxygens. And how many valence electrons does oxygen have? Anybody want to type that in? Or just speak out? You're welcome to unmute yourself if you like. How many valence electrons does oxygen bring to the table? 6, exactly. All right, so we got 6 times 2, that's 12, plus 4. It gives us 16 valence electrons, or 8 pair. Okay. And then let's do the last one, which is that, by the way, NH3, that's a formula for ammonia. Okay. So nitrogen is in group 5. We got 5 valence electrons. Hydrogen, there's 3 hydrogens. Each one brings in 1. And so that is a total of 8 valence electrons, or 4 pair to work with. Okay. And so those numbers that we just calculate as far as valence electrons are the numbers we have to work with. We cannot remove the valence electrons, or we cannot just arbitrarily add. For the first one, we got 10 valence electrons, or 5 pair to work with. Okay. And so we can very quickly draw because we know the carbon's a central atom, so we can very quickly just draw carbon, excuse me, that. We can draw that structure real quick. Okay. Well, that takes care of 2 pair. We have 5 pair to work with right here. Okay, we have 5 pair to work with. We took care of 2, and so now put the other 3 anywhere you want, except on the hydrogen, because the hydrogen now is full. Remember, hydrogen has a duet. It's made a bond already with carbon. It's got 2 electrons being shared. So we can very quickly put the other 3 anywhere we want. We can put them, I'm just going to arbitrarily just put them here. And I'm just drawing the lines. Okay. Now, how many lines do we have? 1, 2, 3, 4, 5 pair. That is what we got to work with. Okay. Now you go back and check the octet. Well, we can see hydrogen's happy, so we can't do anything else with hydrogen. How many electrons are around carbon the way I drew it? Can anybody tell me how many carbon, the way I drew carbon right now? Can anybody tell me how many electrons are around carbon? Just carbon itself, whether it's shared or not shared. But how many lines do you see around carbon? No, try again. Oh no, I stand corrected, Abigail. You're right. Both of you, Sonia, you're 6. Exactly. How about around nitrogen the way I wrote it? Same number, right? I got 2 red ones and the blue ones. So that's 6. And so in both cases, I cannot, the octet is not full. So this is where you start making double bonds and triple bonds, okay? Because you start taking what you have and create a bond between 2 elements. So we're going to take 2 of those red lines, 2 of those pairs, and create a triple bond, okay? And when that occurs, that's the structure that we come up with, okay? Hopefully not too much junk around it. Let me try to get. Ah, it's not like, oh, there we go. Okay. And so count all the valence electrons for that structure. We got 1, 2, 3, 4, 5 pair, okay, which is what we calculated, okay? So that is the structure. Now, anybody want to take a guess at what the general formula is for HCN? The general formula. Remember the general formula, ABE? Anybody want to take a guess what that is? Okay, A is carbon. So we always have an A. But B in this case is a nitrogen and a hydrogen. So B becomes what? 2, subscript 2, AB2. Okay, so the general formula is AB2. Okay, A, B, subscript 2. Okay, so we can go to back to the shapes table and look for AB2. Do we have an AB2? Sure enough, that very first entry. Okay, right there, AB2. Here's carbon in the middle. That bond angle is 180 degrees. The general shape is linear. Okay, very linear. All right, let's go back to the structure. All right, I lost my other format. All right, and now look at the second entry. I think we calculated 13 lone pair for CHF3. Okay, if we go through the exercise again, you can see we come up with, count to make sure there's 13 pair, 3, 6, 9, 10, 11, 12, 13. There's still 13 pair around that molecule. Okay. Anybody want to guess? And notice that on the fluorine, they have lone pairs. They're denoted by 2 dots. You could have a line there. That's okay. Both are acceptable. But those are lone pair because they're not bonded to anything. They're sitting on the fluorides. But there are no lone pairs on the central atom. So what do you think for CHF3 is the general formula? Anybody want to take a guess? The general formula for CHF3. Go ahead and type it in. How about it? We start with A. A, it's got to be A. A is always there. Now, how many atoms are bonded around carbon? There you go. You got it. AB4. That is correct. That is the general formula for AB4. And so now we go back to the shapes table, look for AB4, and guess what? There it is, third entry down, AB4. It's tetrahedral, and it's 109.5 as far as bond angle. That's a very nature. A lot of the compounds on nature have that structure. Structure 109.5. Okay, so let's go back. Now we've got carbon dioxide as the next structure. Okay. Anybody recall how many valence electrons we calculated for CO2? Okay, carbon brings 4. Oxygen brings 6. There's 2 oxygens, so that's 12, correct? Plus the 4. We have 16 valence electrons for carbon dioxide, or 8 pair, right? And look reasonable? Let's try it again. Oxygen has 6 valence electrons. There are 2 oxygens, so that's 12 valence electrons. Okay, carbon has 4, so 12 plus 4 is 16. We got 16 valence electrons, or 8 pair. And since we're given that structure here, we can very quickly type in O, carbon, and then make a bond with oxygen. Okay, because we got 8 pair to work with. 8 pair electrons. We took care of 2 of them right there. Okay, so that means we got 6 to work with, and we can put those 6 in where you want. I'm just going to start from the outside, work my way in. I'm going to make 1 there, 1 there, 1 there, 1 there, 1 there. Normally we got the board to work with if we were, doing face-to-face class, but this makes it a little more challenging. Okay, and then go double check, make sure we still have 8 pair all the way around. So yes, we do. We got 8 pair. Remember, we can add more or less. Now go check the octet. Each of the oxygens are happy, correct? Because there's 8 electrons around each oxygen, the left one and the right one. But carbon only has 4 electrons. And so this is where we start making double bonds. So we can take a pair from each of the oxygen, create a double bond, and we end up with a structure like this. Double bond there, carbon, double bond there, and oxygen. Okay? And we got a lone pair there, lone pair there, lone pair there. Do we still have 8 pair? The final formula. Yes, we do. Okay, now is the octet fulfilled for everybody? Oxygen still has 8 electrons around it. 2 of them are lone pair, and the other 4 are bonded, okay, to the carbon. There's 8 around the carbon, 2 double bonds, and there's 8 around the other oxygen on the right-hand side, 1 double bond and 2 single pair, okay? So now the octet is fulfilled. We got 8 pair. What is the general formula? What do you think the general formula would be here? Anybody want to take a guess? AB2, exactly. And it would be just like HCN, AB2, and we'll have a linear geometry. All right. Nitrogen. Nitrogen has, for ammonia, NH3. Here's the structure for carbon dioxide. Nitrogen has 5 valence electrons and then 3 coming from each hydrogen. So we have 8 valence electrons or 4 pair. Okay. And if you go through the exercise, we come up with this formula here, where there's still 8 valence electrons around the nitrogen, 2 around each of the hydrogens. What will be the what would be the general formula for this species, ammonia, NH3? Anybody want to take the guess here on this one? No guessing. It's right there in front of you. Obviously, it has A. How many atoms are bonded around nitrogen? 3. So B would be 3. Does a central atom have any lone pair on it? Yes. Okay. With that information, what does that tell you about the general formula? Exactly. AB3E. Exactly. So then we go to the shapes table. Notice something? There's a lone pair on the central atom. Automatically think polar. We talked about that earlier, polar. Okay. And so we go to the shapes table. Look at AB2E, which is the 4th entry down. Okay. And it has a bent, also has a bent shape. Okay. Oh, excuse me. Second to the last entry is AB3E. Okay. That's called trigonal pyramid. There's a lone pair. Because the lone pair takes up space, there's 2 electrons. That bond angle gets squished in. So that bond angle is much less than the standard 109.5. Okay. All right. That's good. Let's continue. So this is how we come up with structures based on the number of valence electrons. And then from the number of valence electrons, we start putting them together so the octet is fulfilled, or the duet when it comes to hydrogen. And then based on that information, we can get the general formula, and that tells us information as far as the bond angle and so forth. Okay, so we have what are called polyatomic ions. We are going to, let me pull these up real quick. We're going to use this quite a bit. Okay, the polyatomic ions are on the periodic table. Now, I see the bottom left side here on your periodic table. These are called polyatomic ions. The thing to remember about this is that these guys, right here, these polyatomic ions come as a unit. Okay, we don't separate them. So you see the first one up there, NH4, and it's got a plus charge. These are ions. Okay, they are covalent compounds, but the nature of the beast is such that they're put together with charges on them, which then makes them ions. Okay, and so there's only one cation, that's the ammonia, and that is nitrogen with 4 hydrogens bonded around it. And then we have other ones, acetate, hydroxide, the cyanide, so on and so forth. So there's no need to memorize them. They're sitting there for you. Thing to remember is when you need to use them, because they're polyatomic ions, if we need to use more than one, we have to put parentheses around the whole unit and then put a subscript to add numbers more than one. Okay, we don't separate them. So we can also figure out the Lewis dot structure for these polyatomic ions. Okay, and the step is essentially the same with one difference. Because they have charges, we're either going to add an electron based on the charge they have. So they got a +1, then we add an electron, or we're going to take an electron off based on the charge they have. Okay, and so if it's a negative polyatomic ion, we're going to add electrons to the final electron count, the valence count. And the number we add depends on the charge. So if it's a -1, we add 1. -2, we add 2, etc. Okay. If it's positive, we're going to subtract one number from the valence electrons. Okay, so positives, it kind of turned around a little bit. Negative, add an electron. Positive, subtract. And then we put brackets around the whole picture because it is a polyatomic ion, and we add the charge in the upper right corner of that bracket. So let's try this one. This is the cation ammonium. I just showed it to you on the periodic table. There's nitrogen and 4 hydrogens bonded around it. We count the valence electrons like we normally do. Nitrogen brings in 5. Oxygen brings in 4 because of 4 of them. So that's 9. Right there tells you if you get an odd number, notice the ones that we were doing before, we always ended up with an even number. But the fact that you get an odd number should tell you, should be a flag. Do I need to add or subtract? Okay. So in this case, because it's a positive polyatomic ion, we subtract. Okay. And so we have 5 from nitrogen, 4 for the hydrogens, and then because that's a positive charge, we take 1 out. So we have 8 valence electrons or 4 pair. Okay. And that is the formula. 4 pair. That means that the 4 hydrogens are bonded around it. It has a general formula of AB4. We can do the general formula like we did the others. Okay. So it's tetrahedral in shape. And we put the brackets around it with the plus charge to designate it as a polyatomic ion. Okay. Let's try these. These are kind of interesting here. Now, of course, we don't know what they are. We'll eventually get the naming of them. But here, the upper left corner, you got bromine as a central atom. And then there's 3 oxygens bonded around it. Okay. And it has a negative charge. Okay. And then bottom left corner, we have sulfur as a central atom and 4 oxygens bonded around it with a -2 charge. And then the one on the right, we have cyanide. It's the polyatomic ion where we have carbon and nitrogen bonded to each other, but it's got a negative charge. Okay. So the process we do is same. Bromine is in group 7. So it has 7 valence electrons. Oxygen, there's 3 of them. Okay. It's in group 6. So we're going to bring in 18 valence electrons. And then because it's a -1 charge, it's an anion, we subtract 1. Okay. Now, if you forget to subtract or add, when you do the structure, you're either going to be short a pair of electrons and you can't make double bonds to correct it, or you're going to have an excess number of electrons. So that's a good flag that you maybe forgot to subtract or add the electrons depending on the type of polyatomic ion. All right, so then it gives us 13 pairs. We can very quickly put bromine in the center, put in the 3 oxygens around it, okay? And we end up with a lone pair on the bromine, okay? Its general formula is still AB3E, and we can look at the structure on that. Don't forget the brackets with a negative charge. Okay. Now, sulfate, the bottom left corner is sulfate. Sulfur has 6 valence electrons due to its position in the periodic table. There's 4 oxygens. It's a total of 24 valence electrons. It's got a -2 charge. So we're going to add 2 electrons. Okay. It gives us a total of 32 electrons or 16 pair. Sulfur is a central atom, so we can quickly put sulfur in the middle and then quickly bond 4 oxygens around it, and then add the rest of the valence electrons, and that is the structure that you come up with. Count the valence electrons in there, you'll see there are 16 pair. The same is true with the previous example. You'll see there's 13 pair in there. Okay, remember that's what we got to work with. We can't subtract or add. For the sulfate, which is the bottom left corner, the general formula would be AB4, just like we did before. It would be a tetrahedral shape. Okay. Finally, the cyanide. This is cyanide. We have 4 valence electrons from carbon, 5 from nitrogen, and it's a negative charge, so we could add 1. So we have a total of 10 valence electrons or 5 pair. In this case, there's only 2 atoms, so there really isn't a central atom. We just put them together. Okay. Once you do that, it's a matter of adding those electrons and in such a manner that you need an octet, and you end up making a triple bond with 2 lone pair on the one on a carbon and one on a nitrogen. And don't forget the bracket for the negative charge. Okay. And this is just simply linear. Okay. You only got 2. Anytime you got 2 items, it's simply linear in structure. Okay, now what this is all about is something I just introduced, and I told you, when you got a valent, when you got lone pair of electrons, those electrons are negative charge. There's 2 in the orbital, so they're going to repel each other. That has an effect on the structure, and this is what all that's about. Fancy name, valence shell electron pair repulsion, or VSEPR. All that means is, okay, the electrons are being negative, they're going to repel each other. And that's going to have an effect on the overall structure of the compound. Okay, in the 3-dimensional mode. Don't forget that we are in 3-dimensional world. Okay, and this is what that general formula I was talking about. A represents the central atom, B represents all the outer atoms bonded to the central atom, and E represents any lone pair on the central atom. That's important. Only lone pair on the central atom. We don't care about the lone pair on whatever's bonded to the central atom. Okay, so here, anything is diatomic. Okay, all the diatomic compounds, they're linear. Anything with just two atoms put together had the linear structure. There's no other kind of structure they could have. Okay. This is a good example of, again, this is a covalent bond. They're both chlorides. Remember we talked about electronegativity? There's an equal sharing. That solid bar in the middle represents a bond between the 2 chlorides, okay, bonded to each other. Okay. There's an equal sharing because the electronegativity is equal. And so this guy would be a non-polar species. Non-polar. We'll get a lot more to say about that. The AB2 was linear. We went through the carbon dioxide to come up with the formula. Okay. 180 degrees. Then we have this. This is a structure of formaldehyde. You may be familiar with formaldehyde. This is what it looks like. Okay. This is called AB3, trigonal planar. Okay, got 120 degrees all the way around the central atom. Okay, tetrahedral. This tends to be the most common structure of compounds out in nature. Bond angle of 109.5. Okay, and then we have the AB2E. which is the bent, as a lone pair in the central atom. Okay, you would think that, SO4, this is called sulfur dioxide. If I were to write CO2, you would think carbon dioxide. Remember carbon dioxide, we just did it? It became linear. But the difference here, sulfur dioxide brings in extra valence electrons. It's a different group. And that valence electron must be on the central atom. Okay? And what did I say about anytime you have a lone pair in the central atom? You have a polar compound. Very polar. Sulfur dioxide. Okay, and then we had the trigonal pyramid. An example, this is ammonia. Okay, we went through that example. Again, polar. And then the AB2E2, good example of this is water. Very, very polar. Water is the most polar species that we have. Okay, basically, kind of summarizes. Says, given any covalent molecule or polyatomic ion, you should be able, if necessary, draw the electronic dot structure, and from that dot structure, determine the shape and the bond angle. That comes from the shapes table. Okay, that's important. So you might want to practice on these here, and maybe next time we'll bring it. We can do it in class or during the office time on Fridays. pH3 and ozone. Try those. Okay. All right. Which brings us to bond polarity. This is something I just essentially started talking to you about things we're talking. When we talk about bond polarity, we're talking about covalent bonds. And when you have two species that are bonded together, and the electronegativity, remember the electronegativity is a measure of the affinity to pull electrons toward itself. Okay, and if the electronegativity of two elements are bonded together in a covalent bond, if one of them is greater than the other, it's going to have a tendency to pull that electron density away. What that results into what we call a polar bond. You're either going to have a nonpolar or a polar. Okay, and it's all related to electronegativity. And recall that aspect, fluorine is the most electronegative element. So that's your reference point. So if we want to compare the electronegativity of, let's say, two elements that are bonded together, like using the periodic table, using carbon and nitrogen, and you want to say, well, which is, if it's a bond between carbon and nitrogen, and which is more electronegative, we simply find its position relative to fluorine. In this case, nitrogen is closer to fluorine, so nitrogen is has a higher electronegativity. What that tells you is when they make a bond, carbon and nitrogen make a bond, covalent bond, that nitrogen would tend to pull the electronegativity toward itself. The result is nitrogen will have a more negative flavor, if you will. We'll have another name for it in a minute, than carbon. Carbon now, because the electrons have been pulled away from it, now will have more of a positive flavor. So we end up with a bond that on one end has more of a negative property, and at the other end will have more of a positive property. And that's what we mean by a dipole, something that has two poles like a magnet, positive and a negative in the magnet. Now, and that aspect is very important with respect to chemistry, because it's a driving force for a lot of chemical reactions. Without that, things won't happen. All right, so it's a pole. A good example of this occurring is, I'm sure you've done it or seen it done. You take a balloon, blow up a balloon. You can try this at home if you've never done it. Blow up a regular old balloon, and then take that balloon and rub it on your head. Okay. Well, what have you done by doing that? Your hair is full of electrons. Some days you got a lot of electrons. You have a bad hair day, your hair is sticking up like this, right? Okay, what you have done is by rubbing the balloon on your head, you have transferred the electrons onto the surface of the balloon. Okay? Now you have electrons that have a negative charge, right? Now, everything on you has electrons. There are electrons on the surface of my shirt here. And so when I bring that balloon close to the surface of my shirt, it causes those electrons on the surface to move away because the electrons repel each other. The result is it creates a surface on my shirt that's more positive in nature. And the balloon comes in close enough, it will attach itself to my chest and it will stick there because you have created a dipole area. And that's why that balloon sticks to your shirt. You have forced those electrons away from the surface, creating a positive area. And so the negative area of the balloon is attracted to the positive area of your shirt, and that balloon sticks. Okay? And that's what we're talking about. We're causing electrons to move, or they're being moved because of the electronegativity of the bond. So go back and refresh your memory about electronegativity. We talked about it in the previous chapter. Okay. Now, when something to put in long-term memory, when you have a bond between carbon and hydrogen, it is a nonpolar bond because carbon and hydrogen, as far as electronegativity, is equal. Okay, essentially equal, at least for us here at Chem 130. And so whenever you see carbon hydrogen, think nonpolar. Okay. All the noble gases, they don't have electronegativity. Why? The octet's full. There's no electronegativity value to that. Okay. So that was a trend, left to right increase, bottom to top increase, all directed toward fluorine. Okay. All of the diatomic molecules have no fear of ice cold beverage, plus the carbon hydrogen bond is nonpolar. Okay. Including the carbon hydrogen bond are nonpolar because there's equal sharing of those electrons in that bond, equal sharing. All right. Always consider, oh, let me clear my stuff here. Okay. When we have two different nonmetals, with the exception of carbon hydrogen, we have a polar covalent bond. Okay. So we have two bond types, ionic and covalent. Under the covalent area, you either have a polar or nonpolar. When the elements are the same in a covalent bond, it's a nonpolar bond. When they're different, with the exception of carbon hydrogen, there is a polar bond because it's driven by the electronegativity. All right. So such bonds like carbon and oxygen, okay, hydrogen and chloride. Notice I didn't say carbon, hydrogen and chloride, sulfur and fluoride, silicon and nitrogen. All of these have polar bonds. Okay. Polar covalent bonds. And the result is, like I mentioned earlier, because of the unequal pull, you created these areas of negative and these areas of positive. And we denote that by the symbol here called, it's either going to be partial positive and partial negative. Okay. And we have what we call a dipole arrow shown here in the bottom of each example here, where you have an arrow going, in this case from carbon to fluoride. There's like a little positive on that arrow on the carbon side that represents the partial positive side. okay? And the fluoride, being the most electronegative, is going to pull those electrons toward itself. So it creates has a lot more electron density around it. So it creates a partial negative. We're not saying that you create a full charge. Ionic compounds create a full charge, a full sodium chloride, a full positive charge on sodium, a full negative charge on the chlorides. For covalent bonds, you're only creating a partial, okay? And by the nature of the bond, it is built into the bond. Nature of the bond. Now you can imagine now, with the first example, CF, that it can interact with another molecule because the partial negative will interact with the partial positive of another molecule. Like magnets, magnets, you can line them up. Dozen magnets, the north hits the south, and all the way, line them all up. Same way here. Those are forces that play a big factor on the overall property of these chemicals. All right, so to draw the arrow, we first determine which is more electronegative. In this case, fluoride is a lot more electronegative, so the arrow goes toward the fluoride from left to right, and it has a partial negative. Oxygen and hydrogen, obviously the oxygen is a lot more electronegative because hydrogen is in the far left, group 1 of the periodic table. So our dipole goes from hydrogen to oxygen. And then phosphorus, the chloride, by looking up its position in the periodic table, we find that the chloride is much closer to the fluoride. Therefore, it is a lot more electronegative. And the arrow goes from left to right in this case, okay? We talked about noble gases, so we're well aware of it, okay? Nothing really holds electrons tighter than fluoride. In fact, that's why fluoride is utilized in toothpaste, because it's interacted, it gets incorporated in your teeth to make very strong bonds. All right, so here they're asking you to add the delta notation, that's the partial negative or partial positive, and to add the polarity. Well, carbon, oxygen, we had that example already. Okay, it's going from carbon to oxygen. Nitrogen to fluoride, well, fluoride's the most electronegative, so that's like automatically it's going to fluoride. Okay, left to right. Oxygen and hydrogen, we just did that, it's going toward the oxygen. Carbon and chloride, well, chloride's a lot more electronegative, so the arrow goes from carbon to chloride. And carbon to hydrogen, none. Okay, it's dipolar, it's non-polar. Okay, it's just like the diatomic elements. There is no dipole involved there because the electronegativity of hydrogen and carbon are basically the same. Okay, so they're asking you the question here, are these bonds ionic, or are they nonpolar, or are they polar covalent? Nonpolar covalent or polar covalent? Well, the first question says ionic. Remember the criteria for being an ionic compound? They have to be a metal and a nonmetal, right? And there's only one example here that you have a metal and a nonmetal, and that's sodium chloride. Okay, so everyone else must be covalent compounds, and they are. So the first example, bromine. Both the elements are the same. Okay, so you don't have a dipole. So that is a covalent bond, but it is a nonpolar covalent bond. Phosphorus and fluoride, two different nonmetals, automatically covalent. Okay. Question is which direction for the arrow? Well, it's going to go toward the fluoride, and therefore they're different. They're going to be polar covalent, and the same is true for fluorine and bromine. Okay, it's a polar species. All right. I just realized the time I got over a little bit. Let me stop it here. we'll continue to finish this up. I thought I was going to get it done, but the next chapter is pretty small. It won't take us long to knock it out. And so we'll finish up here tomorrow. And let me make note of page 38. And let me stop